Welcome back. Today's topic is about mechanics and rheology related to ceramic processing systems. Let's start with the mechanics of unsaturated bodies, which means that the degree of pore saturation, DPS, is less than 1. Our story begins with an English scientist, Robert Hooke, who discovered a direct proportionality, called the modulus of elasticity E, between the applied stress sigma and the deformation or strain of a solid epsilon. Under these conditions, the object returns to its original shape and size upon removal of the load and might be called a linear elastic or Hookean body. Ceramic bodies containing a pore phase incompletely saturated with a liquid can be deformed both elastic and plastically when compressed. For those materials, the resistance to deformation is dependent on the cohesive strength and the frictional resistance between particles. When an unsaturated particle system is compressed, the imposed pressure is supported by the mechanical stress at particle contacts and by the pore fluid pressure. The difference between the applied pressure, Pa, and the fluid pressure, U, is called the effective stress, sigma. Let's consider the uniaxial compression of a system of particles confined in a rigid die, as shown in this figure. The force at contacts between particles may be resolved into normal N and tangential T components. A very intense stress at a particle contact may cause local plastic deformation and fracture. The effective stress is lower when the pore phase is saturated with a relatively incompressible fluid that becomes pressurized, as is indicated in this figure. The chart shows a variation of stresses and porosity on loading a compressible, partially saturated particle system. Permeable pistons or dies may determine the effect of drainage of the pore fluid on the mechanical behavior. Materials tend to bond more strongly when in contact. A lubricant reduces the bonding at the interface. This figure shows a so-called Strybeck curve and illustrations of three lubricant regimes. Lubrication is produced by an adsorbed boundary layer of low friction or an interfacial fluid. In fluid or hydrodynamic lubrication, the interfacial lubricating film is thicker than irregularities on the surface of the particle, and the friction is dependent on the viscosity of the fluid medium. A uniaxial press filter cake of a flocculated electrical porcelain body is shown in this figure. The primary compression of filter cake, up to about 1 megapascal, is typical of the collapse of the coagulated clay coating hard particles, which reduces the spaces between particles. Above 1 megapascal, the behavior is typical of clay with a more oriented structure. A typical stress-strain behavior in simple tension of dried ceramic tapes for electronic substrates shows the effect of increasing plasticizer proportion on decreasing yield point, Yp, elastic modulus, E, and ultimate strength. From now on, we will discuss fundamentals and techniques used to determine the rheological properties of saturated systems, that is, with DPS equal or larger than 1. By the way, the term rheology is related to the science of deformation and flow, as coined by Eugene Bingham, an American chemist. On the other hand, rheometry refers to the measurement of rheological properties. Rheology is a science that has been defined by many contributions, including from the supposedly two most important physicists ever, Sir Isaac Newton and Albert Einstein. This graphic shows laminar flow of a fluid between two plates of area A. The bottom plate is fixed. When the top plate is pushed to the right with a shearing force F, it drags the fluid along with it with a speed or velocity v. The relationship between force and area is called shear stress, tau. The velocity gradient dv dy is the shear rate gamma, and the ratio between tau and gamma is the viscosity eta. The SI unit for dynamic viscosity eta, or μ, is the pascalsecond, or millipascalsecond. Note that 1 millipascalsecond is equivalent to 1 centipoise. The kinematic viscosity is defined as the ratio of the viscosity eta to the density of the fluid ρ, denoted by the Greek letter nu, and often measured in the CGS unit centistokes. Just for the records, the unit poise, or poise, was named in honor of the French physicist Jean-Léonard Marie Poiseuille, and the unit Stokes was chosen after the Irish mathematician Sir George Gabriel Stokes. Here is a simulation of liquids with different viscosities. The liquid on the right has higher viscosity than the liquid on the left. For instance, at 25 degrees C, water has a viscosity of 1 millipascal second, or 1 centipoise, while a motor oil would be 100 to 1000 times more viscous. Let's skip to some rheological models. Starting from zero shear stress and shear rate, when there is a linear correlation, the liquid is said to be Newtonian, such as water, and the constant of proportionality is the viscosity. When the viscosity decreases with the shear rate, it's known as pseudoplastic, or shear thinning. When the viscosity increases with the shear rate, it is dilatant, or shear thickening. If the yield stress is higher than zero, and there is a linear correlation between shear stress and shear rate, we call it a Bingham or plastic behavior. A general equation describing those behaviors is the so-called Herschel-Bulkley model, where tau is the shear stress, gamma the shear rate, tau y the yield stress, k the consistency index, and n the flow index. If tau y is larger than tau, the Herschel-Bulkley fluid deforms as a solid, otherwise it flows as a liquid. For n lower than 1, it is shear thinning, whereas for n greater than 1, it is shear thickening. If n equals 1 and tau y equals 0, this model reduces to the Newtonian fluid. Ideal elastic or Hookean materials strain when stretched and immediately return to their original state once the stress is removed. Ideal viscose or Newtonian liquids, like water, resist shear flow and strain linearly with time when a stress is applied. Viscoelasticity is the property of materials that exhibit both elastic and viscose characteristics when undergoing deformation. Ranges of shear rate encountered in ceramic processing operations are indicated in this figure. Rheological data are more relevant when the viscosity is determined in the range of shear rate of the process. The rheological behavior discussed so far was assumed to be independent of the shear story and shearing time. For some materials, the viscosity at a particular shear rate may decrease with shearing time. This behavior, called thixotropy, is commonly observed for shear thinning materials, when the bonding of molecules or particles break apart with the time during shear flow. A few materials exhibit an increase in viscosity with time when sheared at a constant rate. This behavior is called rheopexy and may be expected when agitation enhances bonding between structural units in the suspension. Thixotropic behavior in ceramic slurries is often reversible. For a thixotropic material with a yield stress, the apparent yield strength is higher after the suspension has been at rest and a particle structure has reformed. This higher apparent yield stress after a period of rest is often called the gel strength. Heating increases the specific volume and reduces the viscosity of simple liquids. The variation of viscosity over a limited temperature range is approximated by the equation known as the Andrade equation, due to the English physicist of Portuguese origin, Edward Andrade. In this equation, A and Q are constants for a particular liquid. The viscosity of a suspension, eta S, is greater than the viscosity of the liquid medium, eta L, in the suspension, and the ratio is referred to as the relative viscosity eta R. For a very dilute suspension of non-interacting spheres in a Newtonian liquid, the viscosity for laminar flow is described by the Einstein equation as a function of the particle volume fraction. A more general equation for the viscosity of a suspension of non-spherical particles introduces Kh as the apparent hydrodynamic shape factor of the particles. In suspensions of particles with an aspect ratio greater than 1, particle rotation during flow produces a larger effective hydrodynamic volume and Kh over 2.5. Rheological data for suspension of uniform spherical colloidal particles are often approximated by the Dougherty-Krieger equation, where FCR is the critical volume fraction at which flow is blocked. The Einstein equation applies to volume fractions less than 0.01, assuring that the flow around a particle does not influence the velocity field of any other particle. At higher particle concentration, the hydrodynamic interactions between particles become important. In those cases, the Dougherty-Krieger equation may be applied. Some common devices used for measuring viscosity in ceramic suspensions are summarized in this table. The Ford cup is a single gravity device used to determine the timed flow of a known volume of liquid passing through an orifice located at the bottom. The least expensive commercial variant of the controlled rate rotational viscometer is commonly referred to as a Brookfield type. This device measures fluid viscosity at fixed rotation speeds by driving a measurement tool, or spindle, immersed in the test fluid through a calibrated torsion spring. High-precision shear instruments in which the test fluid is sheared under controlled stress or controlled rate conditions are termed rotational rheometers. Most rheometers depend on the relative rotation about the common axis of one of three tool geometries: concentric cylinders, cone and plate, or parallel plates. Here, we may compare simple rheometry devices such as a Ford cup and a Brookfield type viscometer with a complex advanced rheometer, in this case with parallel plates geometry. Now, some exercises on mechanics and rheology. Questions. A pressure of 700 kilograms force per square centimeters is applied to concrete and the pore pressure is measured to be 30 bar. What is the effective stress carried by the particles in megapascals? In figure on page 5, give 3 alternate shaping techniques that offer the possibility of drainage. Explain each one. Compare the Strybeck curve on page 6 with the consistency states chart for a clay water system. The strength of ceramic tape is determined in simple tension. The load at yield is 4 Newton and the sample is 50 micrometer per 40 millimeter in cross section. Calculate the yield strength. In the stress strain chart, page 8, locate the ultimate strength and strain at rupture for the 3 curves. Justify it. Graph the variation of apparent viscosity K with shear rate for power law pseudoplastic material considering N equal 0.2, 0.5, and 0.9. Some clays, including bentonite, exhibit thixotropy. Explain schematically how it happens. Estimate the viscosity of water at 10 and 40 degrees C. Consider A equal 1.25 times 10 raised to negative 3 millipascal second and K over R equal 1970 Kelvin. Calculate and graph the variation of relative viscosity with solids loading when F critical equals 0.55 and KH equals 3.5 using the Dougherty-Krieger equation. Explain why a Brookfield type viscometer cannot be considered a rheometer. That's it for today. See you next time.